Have a look at some questions involving indicators and amino acids. Whenever you see an equation, try and keep in the back of your mind that is just equilibrium. And in that, Le Chatelier applies. So let's have a look here. We've got an indicator, thin or red. And if I go to my data booklet and I've got thin or red here, it's yellow to red and changes about 7.9. So let me just write this up. Yellow to red, 7.9. Okay. So anything less than a pH of 7.9 is going to be yellow. Anything more than a pH of 7.9 is going to be red. So often the question will have something to do with color as well. So what we're seeing here is a dissociation. So this is what we have, and we're in equilibrium. We've got some of this and some of this. Now, we're not really interested in that so much, but we are in this here. So indicators are weak acids in that they form a hydrogen ion or that hydronium as well. So what does that mean? So that means, let's have a look in the acid, an acid solution. So let's say we've got an acid solution and it could be HCl, nitric acid, and ethanoic acid, anything like that. So we're putting it into an acidic solution. And what that basically means, so all of these have lots of hydrogen ions. So what we want to have a look at is what effect would these have on this there? And that just comes back to equilibrium. So we're increasing the concentration of hydrogen ions. Now, what's that going to do with the equilibrium? So if we have a look at this, we're increasing the concentration of that. So according to Le Chatelier, when we increase the concentration of something, equilibrium will shift away from that so that we use it up. So we try and get rid of it and it will move to the other direction. So in this case, in acidic, it's going to move towards the reactants. And in this case here, the reactants are yellow. So maybe I should have written that first. This is the yellow, and this is the red. Okay. So that's going to keep going anywhere where the pH is less than 7.9. Now let's have a little think about if we use a base now. So using some potassium hydroxide, some ammonia, or something like that. Now what that is going to do is that's going to decrease the concentration of the hydrogen because it's going to neutralize. Okay, so the OH minus plus the H plus is going to make water. So we're going to neutralize that. We're going to decrease the concentration of these hydrogen ions from up here. So what that basically means then, so in a base, the equilibrium is going to shift to make more of these hydrogen ions because we've got less of them now. So equilibrium is going to shift in that way towards the products. And the products are red. So what we see there, pH greater than 7.9, it's going to be red. And that's how these indicators work. So let's scroll down and have a look at another thing here. We want to look at how that affects amino acids, because basically it's the same thing. We've got an equilibrium here, but we've actually got a two-way equilibrium. So let's just look at histidine for a moment. So I'm going to draw two equilibrium arrows here, and I'm going to open up my data booklet. I'm going to find histidine. Histidine. There we go. Oh my goodness. How am I going to draw that? Oh, let's quickly draw that. So we're going to have isn't a single one here. Is the get rid of that. It's a hydrogen. Complexity. Something like that. Not precise, but the bonds around wrong. But anyway, you get the idea. Okay. So what we actually have here is what we call a zwitterine. So let me have a look here as well. Histidine, this is the important bit as well. Now it has an isoelectric point of 7.6. So that means at pH of 7.6, it's going to be in this form here. And it's going to form what we call a zwitterine. Now what a zwitterine is basically a positive and a negative. So I'm going to take this hydrogen, and I'm going to put it over here. So basically, let's remove that. That is one. And remove that. And get rid of this two. And so now we've got three hydrogens here. So this is going to be positive. And we've lost the hydrogen, so it's going to be negative. So you see how we have a positive and a negative at the same time. The charges balance out, but we have a positive and a negative on at the same time. Completely neutral, but we've got a positive and a negative. Now, at a pH above 7.6, it's going to be the same thing. We're going to neutralize, because this is basic for alkaline, we're going to neutralize that hydrogen ion. So we're going to go back to this. However, we're going to keep the negative oxygen and the stuff to try and just quickly use them. Okay. So in a base above that isoelectric point, it's going to be the negative form. And below 7.6, where it's an acidic and an acid, we're going to keep the positives, but notice we have no negative over. So we just have that positive side. Over here we've got the negative, and in the middle we've got both. So this is a positive form. This is the negative. Now if we did electrophoresis, put a charge through it, this is going to go or move to the negative electrode, isn't it? Because it's positive. And this one is going to move to positive electrode because it's negative. And that's another way that we can separate out these amino acids based on equilibrium, based on pH, based on acid being positive and base being negative.